Hi everyone, this is lesson 2-1, Power and Rational Functions. In this video, our learning target will be for students to be able to graph and analyze power functions. In graphing and analyzing power functions, we need to look at functions that have rational exponents. Remember that a rational number is a number that can be written as a fraction. So when we talk about what rational exponents are, right here, rational exponents, when we're looking at our function, our exponent is going to be a fraction. What we're going to be asked to do here is graph f of x equals x to the 5/4 power. We're going to describe the domain, range, intercepts, and behavior, continuity, and where the function is increasing and decreasing. So what we're going to be doing here is graphing the function. So if I go to Desmos and graph x to the 5/4, I will type in y equals x to the 5/4 and then copy and paste my graph here. Now that I have copied and pasted that graph, you can see that you have the function y equals x to the 5/4. And what we need to do is we need to analyze its domain, range, intercepts, and behavior, continuity, and where the function is increasing and decreasing. Now the domain, if you can see, the graph starts at the origin, right here at 0, 0. And so the domain, since the function increases to the right, as the graph only moves to the right, you can see that this graph right here has a domain that's contained in the first quadrant. So our domain is going to be 0 to infinity. And if you are looking at the range, since also the y value is the lowest at the origin there, you can also say your range is 0 to infinity. And we're going to include 0 because if I input 0 to the table, 0 to the 5/4 power is actually 0. And so then when we're looking at the intercepts here, because the graph starts at the origin, the x and the y intercept are both at 0. So you could say x equals 0 and y equals 0 for the intercepts. The end behavior here, you only are going to have one end behavior because the graph is only moving to the right. The graph abruptly stops at 0. So you're only going to have one infinite end behavior, I should say. And so we're going to say x approaches infinity for the function is equal to infinity because the graph is going up. The graph is increasing as the graph x approaches infinity and as the function approaches infinity. And here we have x approaches 0 from the right side of the function, because if we take and approach the function, we can't approach negative infinity because the graph doesn't exist when x is less than 0. But I can say that as I approach 0 from the right side of the graph, that my y value is equal to 0. So I'm going to say my limit there is going to be equal to 0. As x is approaching 0 from the right of the function, you get a limit of 0. When we are looking at continuity, the function is continuous, but it is only continuous from 0 to infinity because the domain is restricted. Again, over here we decided the domain was from 0 to infinity, so the function is only continuous for those x values that are part of the domain. Our increasing and decreasing, the function is increasing only. The graph is going upwards here, so if I'm going up and tracing the graph, the y value is increasing, so therefore you are going to have an increasing value from 0 to infinity, not including 0, because the graph is not yet increasing at x equals 0. So we have analyzed this graph. We have a domain, range, intercepts, the end behavior, the continuity, and where the function is increasing and decreasing. Looking at example B with rational exponents, we have the function f of x equals 4 times x to the negative 2/5. So we have a negative rational exponent here. Again, rational exponent is an exponent that's a fraction, and in this example, the exponent also happens to be negative. So what we're going to do is we're going to graph this function, and I'm going to graph y equals 4 times x to the negative 2/5 in Desmos, and then I'm going to analyze that function. So looking at the graph here, if we look at the domain, there's a break at x equals 0. You can tell that there's a break at x equals 0 because one thing you could do is evaluate the function for x equaling 0. And if you take 0 to the negative 2/5 power, that's the same as saying 1 over 0 to the 2/5 power. And 0 raised to any exponent is equal to 0. So I have 1 over 0 there, which is undefined. So looking at this example here, we have a domain. Right? We have a domain here that excludes 0. So we can say the domain is from negative infinity to 0, union 0 to infinity. The range, it looks like the ends of this graph here, they flatten out as we go to the edges. I wonder if they approach 0 or if they approach another number for y. So what I need to do is I need to evaluate what my end behavior is doing first to determine what my range is, because I'm not sure exactly what y value that this graph levels off at. So what I'm going to do is I'm going to determine my end behavior first, the limit as x approaches infinity of the function, and the limit as x approaches negative infinity of the function. I'm going to go into Desmos and type in some really big number for x, and then a really big negative number for x, and see what my y value is. So it turns out that the ends when I approach infinity for x, so when I plugged in a really big number for x into the table, my y value is approximately 0. And the same thing happened as I approached negative infinity, the y value approached 0. Now what this tells me is that this axis, the x-axis here, is the line or asymptote that the graph is approaching, which means that my range, the lowest y value I'm going to reach, is approximately 0. So when I draw my range, or when I write out my range, I can say the range is from approximately 0 to infinity, not including 0 because the graph will never intersect the x-axis. So looking at that, we've calculated the domain and the range, and we've done the end behavior. The graph is discontinuous. If we look at the continuity, the graph is discontinuous because there is a break at 0. So there's an infinite discontinuity at x equals 0. Right? So there's an infinite discontinuity there. And if we look at the where the function is increasing and decreasing, the left half of the graph is increasing and the right half of the graph is decreasing. So we'll say this half of the graph is increasing, this part is decreasing. So what that tells me is that the function is increasing from negative infinity to 0, yet it's decreasing from 0 to infinity. Remember, we use the x values for the intervals to describe increasing and decreasing functions. So we've taken care of the increasing and decreasing. The only thing left is to see where the graph has intercepts, and the graph approaches x equals 0. Since we can't use x equals 0 as a value in our domain, that means we do not have a y-intercept. And because the graph approaches the x-axis and never intersects it, that means we never have an x-intercept. So the intercepts here for this function is none, right? We have no intercepts because the graph never intersects the x and y axis. And if I substitute in 0 for x, like I did over here at the beginning, we saw that y value is undefined. So we have analyzed this rational function. Go ahead and move on to the check for understanding. All right, to check your understanding here, you're asked to describe the continuity of the function f of x equals 4x to the positive 2/3. You have 4 choices for your answer. That a is continuous for all real numbers, which would be it's continuous from negative infinity to infinity. Is it continuous from negative infinity to 0 and 0 to infinity, implying that x cannot equal 0? Is it continuous from 0 to infinity? Does the graph only exist from 0 to infinity? And also continuous from 0 to infinity. Now, the difference between these two is that x is not included in this interval, and 0 is included in this interval. So when you decide your answer, you have to decide whether the function is defined at 0 or not defined at 0. If the function is defined at 0, you include 0 in your interval where it's continuous, and if 0 is not defined, x equals 0 is not defined for the function, then you do not want to include it. Okay, so go ahead and graph this function and determine its continuity, and press submit when you're done.